So welcome back to this public lecture for the Summer Institute in Machine Learning in Economics. We are very fortunate to have Jens Ludwig present on algorithmic fairness today.
Great. Let me see. Can you see my slides? Okay. Yeah, perfect. So I've never heard the term tribe of Sendel co-authors before Bo used that. So I'd like to think of everybody as the tribe of Jens co-authors. So I've been spending the break kind of reflecting. So what I wanted to do in this talk is step back and pull together some themes around algorithmic bias that I think have come up in the presentations that you saw just now from Danielle and Bo. But before I do that, let me just start off a little bit. You'll get the slide deck. Here's some background materials for the talk. So it's based on a bunch of papers that we've been writing over the last 5 years or so. I wanted to start off talking a little bit about building on what I said yesterday at the introduction about why I'm so excited about prediction policy problems. And one of them is I can see out in the real world all of the social impact arbitrage opportunities that we see over and over again in all sorts of different policy sectors. I was trained as a garden variety economist. I went out into the world with my research centers looking for policy problems to solve that hinged on a causal inference. And as we were talking more and more to policymakers, we could see that a lot of the policy problems they were wrestling with were really ones that hinge on a predictive inference rather than a causal inference. And we can also see from a large body of psychology research going back 50 years that humans are just terrible at prediction. And we have lots of reasons to believe that AI can be much better. And we also think that economists have something to contribute on these issues because of the intellectual arbitrage opportunities that we've been talking about over the last 2 days. So let me just I wanted to start off giving you a couple of examples of the sorts of things that we've been working on. So for those of you in the US, you know that there's a large rise in gun violence in almost every major American city. In places like Chicago, compared to 2019, gun violence is up something like 50 to 70%. Chicago's not alone in that. There's a huge demand right now for non-criminal justice responses to the gun violence problem. So social programs, things like there's something called Ready in Chicago. When you talk to NGOs that are delivering these sorts of programs, what they say is the guys who are at highest risk, who most need help, are the ones who are least likely to walk in our front door. So they want to go out and do active recruitment. That raises the question of how exactly you identify these high-risk guys to go out and recruit. And we've been working with the NGOs in Chicago using machine learning for that sort of targeting exercise. A related example, on the heels of this once-a-century pandemic, there's massive concern about learning loss, among economically disadvantaged kids in particular, concern that these kids are never going to make that up, given the way the US school system is structured. So there's huge interest in using recovery plan dollars to target academic remediation, and we're working with school districts to think of ways to target high dosage tutoring. That's actually a problem that sits at the intersection of predictive and causal inference, as you guys have already heard. As you also know, one of the big public policy challenges that the United States, not just the United States, has right now is around questions of policing and police misconduct and police reform in particular. In my hometown of Chicago, one of the most noteworthy instances was the shooting of teenager Laquan McDonald a few years ago by Chicago police officer Jason Van Dyke. And one of the things that I think is particularly noteworthy about this example is the Chicago Tribune did an interview with his wife, who said that she could see a few years before the shooting signs that he was being changed by his time on the police force, which raises the question of whether we could use all of the rich administrative data that police departments collect on officers to predict which officers are at highest risk for misconduct and then intervene and do something to prevent these sorts of adverse events before they happen in the first place. Let me just give you one more example. In 2017, New Jersey implemented some landmark criminal justice reforms that got both the left and the right some things, including the use of predictive algorithm to inform pretrial release decisions. And what we've been seeing there are sizable drops in the number of people held in jail pretrial in New Jersey after the reform, alongside sizable drops in crime as well. So this looks like a success, but there are a bunch of concerns that New Jersey has about aspects of the reforms that are not going quite as well as they would like. So we're working with them to strengthen the predictive tools that sit at the heart of the reforms. So lots and lots of policy applications that we're very excited about out in the world. And as we think about the potential for further impact with these sorts of algorithmic prediction projects, it's clear that the biggest challenge, the biggest substantive challenge to be solved, and the biggest challenge to further scaling this approach to solving policy problems, if we can't successfully solve it, are concerns about algorithmic bias. The ProPublica article that came out 5 years ago, I think, was the most noteworthy example of this, but there have been lots and lots of concerns expressed about algorithmic bias. You can see those concerns filtering down to public opinion. You can see a majority of Americans think that algorithms will be intrinsically or unavoidably biased. This is in the criminal justice space, but you can see that if you ask people about the use of algorithms in all sorts of other policy applications as well. So what I wanted to do in this talk, it's just to say bias is, I think, sort of the biggest challenge in thinking about diffusing algorithms into policy relevant domains. What I wanted to do in this talk is pull together some thinking that we've been doing over the last few years about algorithmic bias and what it means, how to address it, where it comes from, and what economists have to contribute to this. And then what I wanted to do at the end is give a real world example of what we've seen when we go try and apply this approach out in the real world. Okay, so let me start off with a tale of two studies. And since I'm a member, I guess a card-carrying member of the tribe of Sendel co-authors, it's fitting that I start with one of Sendel's studies. Let me start off with a study in economics that Sendel and Marianne Bertrand did 20 years ago to identify discrimination in the labor market at a time when all HR decisions were essentially made by human beings. And so this is a group of economists, so you're all well aware of the causal inference challenges there associated with measuring discrimination in hiring. And the innovation in Sendel and Marianne's paper was to figure out a way to overcome the omitted variables concerns for identifying discrimination by sending out identical resumes to firms, but randomly changing the name at the top of the resume to signal the applicant's race. Okay, and so this is because the resume is the only information that the firms can see, and making the callback decision, we've solved the inference challenge around how much is due to race versus other omitted characteristics of job applicants that we can't see in our data set. And what you see in this case is a 50% higher callback rate if the resume has a white name at the top. Okay, and so just a few things that are worth mentioning about this study. One thing that's worth mentioning is when you talk to Sendel or Marianne about this, it took a huge, like a D-Day landing type operation to carry out the study. Lots of RAs sitting in the basement of MIT and Booth School of Business at Chicago, mailing out resumes and setting up lines to measure callbacks and so on. The second thing that is worth noting about this study is even once they detected evidence of discrimination, there's really no way through this sort of research design to learn much more about exactly what is going on in the human's head that's leading to these outcomes. Okay, what is going on inside the black box of the human brain that's leading to these sorts of decisions? And the third thing that's worth noting is, this has led to a cottage industry of people doing resume studies or variants of the resume studies over the last 20 years. And I think one of the other noteworthy findings from that literature is the amount of discrimination that we see in the labor market doesn't seem to have changed very much. Okay, so Sendel and Marianne gave the world this very powerful tool for putting a spotlight to measure the amount of human discrimination. I think with the hope that if we could measure the discrimination, we could do something about it. And over this 20-year window, we haven't actually seen lots of real world change. Now let me contrast that to another study that Ziad and Sendel had come out 2 years ago in Science that was also about detecting discrimination, but in a very different context of what are called care coordination programs. And so what you see in most healthcare systems is that a small subset of patients with chronic health conditions wind up disproportionately accounting for all healthcare costs. And so there are lots of healthcare systems that want to identify these high-cost patients in advance and target them with extra resources to make sure they're coming in for regular doctor checkups, getting their prescriptions filled, whatever it is, to try and reduce very high need medical events. And so to target those patients for this sort of concierge service, or whatever you would want to call it, or care coordination, a lot of these healthcare systems are using algorithms right now. So this is done at scale with literally hundreds of millions of patients around the country. Okay, and so actually, let me. So what would it look like to test one of these algorithms for racial bias? Well, you could imagine, what you would want to see is something like imagine that you plot calibration curves for two groups, one from a majority group and one from a protected class group, like white patients and Black patients. And you have predictions on the x-axis and the thing that you're predicting on the y-axis. And ideally, what you would like to see is the calibration curves for the two groups lying right on top of one another. That is what it means for an algorithm to have similar predictive properties for the protected group and the majority group. And what they saw in the Science paper is something that looks quite different from that. So on the y-axis here, you have a measure of patient health, okay? And as you move up the y-axis, the worse patient health. And on the x-axis, what you have is the algorithm's prediction of patient risk, okay? And what you can see is that the curve for Black patients is very non-overlapping with the curve for white patients. It's substantially above the white curve here, okay? And as a way to think about the magnitude of this difference between the predictions for Black and white patients, the way that these care coordination systems usually work is that they choose some sort of risk threshold for auto-enrollment. So in this case, suppose that it's at the 97th percentile. What you can see is that the Blacks at the margin, at the 97th percentile cutoff, are substantially less healthy or more unhealthy than whites at the cutoff as well. So to get a sense of the magnitude of the misprediction, what you can imagine, and you see this when you look at lots of other health outcomes as well, to get a sense of the magnitude, what you can do is you can imagine replacing healthier whites with less healthy Blacks until the marginal patients that you're enrolling into the care coordination program are equally healthy, all right? So what you could imagine doing is basically taking out, right, removing the marginal white patient who just got enrolled and swapping in the next most risky Black patient, and continuing to do this. So marching down the curve for Blacks and moving up the curve for whites until you have equal risk for the marginal white and Black patients who are enrolled. And if you do that, what you would see would be essentially a doubling of the fraction of Black patients who wind up auto-enrolled. All right, so that's just to say that there's not just bias in this algorithm, but it's very, very substantial bias in terms of its real-world implications. Okay, and so then you can ask yourself, what's going wrong with the algorithm? What is the algorithm doing? Where's the algorithm going wrong? And the clue here as to what the source of the bias is with the algorithm comes from looking at where the algorithm is going right. So what do I mean by that? Okay, look at this graph now here. So the x-axis here is exactly like the one that I just showed you. This shows the algorithm's risk score prediction for patients, again, lower risk on the left, higher risk on the right. And now what I'm doing is I'm replacing the y-axis not with patient actual health, but rather with health utilization or health expenditures per patient per year, okay? And when you do this, all right, so if you think about how Ziad and Sendel are doing the study, they've got data from healthcare systems and they've got the algorithms predictions. They don't have the proprietary information about what the company's actually doing to build the algorithm. That's the company's IP. So you're initially assuming that they're predicting patient health. You can see the curves are miscalibrated. You can redo that calibration exercise for black and white patients using annual patient healthcare consumption. And here you see that the curves are almost perfectly overlapping for black and white patients. All right, so it's very well calibrated, not for patient health, but by patient healthcare utilization. So what does that tell you? So the key insight here is that black and white patients don't have the same relation between health status and healthcare utilization. Whites wind up having better access to healthcare, and at every level of health status, blacks wind up utilizing less healthcare. So accurately predicting healthcare utilization winds up leading to biased predictions for patient health. Or put differently, the algorithm builders built something that was predicting healthcare use rather than actual health, right? So the team thought that they were predicting health. It was predicting utilization. That's usually not such a big deal in health policy discussions. We often use healthcare and health status interchangeably when we're thinking about things like Medicaid policies, right? But here, for this application, they're very different. And it's not just that they're different, it's that they're different in a biased way. Okay, so the reason I think the lesson, so actually, sir, let me then give the coda to this study, and then I'll pull back and give you what I think is the key lesson from this. Okay, so what's relevant is then the final part of this study that's relevant is what happened next after their algorithmic audit. So this paper comes out in Science. They email a copy to the company that makes the algorithm. The company has a holy shit moment. And so Sendel and Ziad and their co-authors point out that you guys have been deploying an algorithm that leads to very biased outcomes, but it turns out to be quite easy to reconstruct the algorithm with a different dependent variable to produce something that doesn't have the same sort of biased properties. And the result is that the healthcare systems and the algorithm manufacturers now are working on updating the algorithm. So if you sort of contrast the resume audit study for bias in human hiring with the algorithm study of bias, with the care coordination study of bias in the targeting algorithm, what do you see? Well, one thing that you see is it turned out to be much easier to uncover bias with the algorithm in a situation in which you can get the data, right? And that's an important caveat. So in a world in which we have the right regulations in place where third parties can access the data that underlies these algorithms, in principle, it can be much easier to uncover bias with algorithms than with humans. The other lesson from this is it's much easier to understand the source of the bias with the algorithm compared to the human mind. And the third lesson I think that comes from comparing these two studies is it's much easier to fix the problem of bias with an algorithm, partly because we're able to diagnose it relative to what's going on with bias within the human mind itself. Okay. So I think that, for starters, is a very useful kind of frame about how to think about human bias relative to algorithm bias in a world in which both are capable of bias. So then let me turn to the sort of the second part of what I wanted to talk about, which is how do we think about or understand where algorithmic bias comes from, okay? I think if you look at the, when 60 or 70% of the American public says we think algorithms will unavoidably be biased no matter what we do, or when you see people in the computer science community dividing themselves up essentially into pro-algorithm or anti-algorithm camps, in some sense, what that's sort of explicitly or implicitly revealing is some view that what's going wrong with these algorithms is intrinsic to the AI technology itself. Like, I think a lot of people have in mind something like HAL from 2001, for those of you who, very few of you are probably old enough to have seen 2001, but maybe your grandparents have told you about that movie, where the guy is on the outside of the shuttle and is asking the computer to let him back in because he's got a leak in his whatever, and the computer says, I'm so sorry, Dave, I'm afraid I can't do that. Like, the AI is doing something above and beyond what the humans intend, I think, is the image that lots of people have. But let's just go back to the care coordination study. What went wrong there? What went wrong there? You can see Sendel made up this slide here. That's why the animation is so flawless here. Let's go back to the care coordination study. What went wrong there? We were making a decision based on some conceptual variable Y star. We thought we were predicting patient health. We were actually using a different variable Y, and the bias between the actual variable and the thing that we thought we were predicting, the measurement error there turns out to be correlated with protected class characteristics like race, gender, and so on. We see this over and over in lots of different prediction applications, like predictive policing, for instance, right? We think that we want to send police in high crime areas. You know, if you think about, like, what is a drug crime? A drug crime essentially tells you that the police are choosing to make arrests in a particular area for drugs, right? So essentially, we're predicting arrests in that case, not crime. And the difference between crime and arrests is very, very likely, or we know is correlated with all sorts of protected group characteristics. And that's another example of something that sits at the intersection of causation and prediction. I think Jan will probably talk more about that later in the workshop as well. And then you just saw two examples of hiring and all the ways in which that can go wrong there. Or these are concrete examples of what we've come to think of as blueprint errors, right? So there's the machine learning engineering that the computer science teaches you to do, but then there are a bunch of blueprint decisions around that. That's basically the stuff that gets handed to the computer scientists to implement the machine learning engineering. Things like, what is the variable that we're actually going to predict? And one of the common sources of algorithmic bias is that the dependent variable is wrong. And one example of that is the measurement error is correlated with race. Here's another example. In the training data, we have the wrong rows. That is, the training data is unrepresentative. And I think one of the most obvious examples of this is all of the problems that we're seeing out in the world with facial recognition technology, right? They're disproportionately built with training data sets that are overwhelmingly white, typically, okay? And a final example is evaluation errors, right? In computer science, they have a term, they have an understanding of what it means to evaluate an algorithm, which is to confirm that it is predicting accurately out of sample. So they have a very well-developed set of procedures to, quote, evaluate algorithms in that sense. But in policy applications, what we're doing instead is we're taking algorithms and deploying them into policy situations where we want to change decisions. And for that sort of evaluation, we need a counterfactual. How does a algorithmically informed decision compare to a purely human-driven decision? And so simply knowing that the algorithm predicts accurately out of sample doesn't give us the type of causal inference evaluation for the algorithm's impacts that we really want. Okay, and so, for instance, like in Sendel's, and more generally, even other dimensions, even simpler dimensions of evaluation, often in this field aren't done correctly. So when Sendel and Ziad send their science paper to the algorithm manufacturer, and they have a holy shit moment that tells you that there was inadequate evaluation before deployment. Okay, so I think the key takeaway here is that when we're looking at the different sources of algorithmic bias, almost all of these wind up stemming from the human build choices or blueprint choices that sit around the machine learning engineering, rather than from things that are going on within the black box of the machine learning engineering itself. And there are principled ways that we can address these problems. Okay. So the third type of the third set of things that I wanted to talk about then is to turn to this. Now we have some understanding that algorithms and humans can both be biased. So I want to turn to the question of whether we think, and now we have some sense for where the algorithm's bias comes from. So then we can consider the question of how to think about whether the use of algorithms will aggravate or ameliorate bias. And so Danielle and Bo showed you some examples of papers where algorithms can reduce bias, okay? And there are lots and lots of examples of New York Times articles and academic papers showing the reverse, okay? And so how do we make sense of what we see out in the world? And I think part of the issue here is that we lack a clear framework for thinking about these questions of algorithmic bias, what we even mean by bias, what the algorithm is being compared to. So I wanted to talk you through a framework that we developed for this AI class that Sendil and I teach at the University of Chicago that I thought was very clarifying for me, and I hope it is equally helpful for some of you as well. And so to see this, let's start with the application that we've been spending a lot of time thinking about, which is pretrial release decisions. So Sendil touched on this briefly in his opening talk yesterday. You get arrested in the court system, or you get arrested in the criminal justice system in the United States. You've got to go in front of a judge within 24 or 48 hours. And that judge makes a decision about where you sit awaiting trial, whether you get to go home or whether you have to sit in jail. And that decision is supposed to be based purely on a prediction of your rearrest risk, either your rearrest risk or your flight risk, okay? And it's a big problem. The United States makes something like 12 million arrests a year. And at any point in time, we have something like 750,000 people in jail, disproportionately people of color. And if you sit in jail, on average, you'll be in there for a substantial amount of time, something on the order of 2 or 3 months, and can be as high as 9 to 12 months. Okay, so let's think about to build up to the framework. Let's think about a very cartoon example for starters to illustrate some of the ideas here. Okay, so let's imagine a little cartoon sort of toy data set here, where we have two groups. One group is disadvantaged, the other group is not disadvantaged. And we have people with prior criminal records and people without prior criminal records. And let's assume that prior record is predictive of rearrest rate, okay? And that we're making pretrial release decisions based on rearrest rates. So let's assume that the prior record is predictive of rearrest rate and disadvantaged status isn't conditional on prior record, okay? And then the one other thing that I want to assume here is that the data that we have, that I'm going to assume for now, is that the data that we have are unbiased, okay? So that these rearrest rates reflect actual criminal behavior. I'll return to this question of what happens when we have bias in the data in a minute, okay? So with this very sort of simple cartoon example, then we can start to unpack some of the things that some of the challenges that we wrestle with in real data and real policy applications out in the world, okay? So just for starters, to remind us, there's no arrest rate difference between the groups conditional on their prior record, okay? But notice in this cartoon example that the disadvantaged group is more likely to have a prior record. So the only thing that differs between the disadvantaged and the advantaged groups here is the share of people in the disadvantaged group with a prior record, okay? And, you know, that, in some sense, that's what it means to be disadvantaged, okay? So that reflects the structural disadvantage that we have out in society. So for instance, there's a large body of economics research showing that educational attainment is one of the strongest predictors of risk of crime involvement. And we know there's also a large body of research in social science showing that there are very large differences across race groups or income groups in the United States in access to educational opportunity. So that would be one reason, for instance, why you'd think that there would be different distributions by prior record. And so when we look at the arrest rate, because of this different distribution, Here, when we look at the arrest rate between groups overall, you can see that the disadvantaged group has a higher arrest rate overall, okay? Now we can ask, with this little cartoon example, what would it mean to choose who to detain in an unbiased way in this little cartoon example, okay? So one candidate definition that we might have for choosing in an unbiased way is for judges to pay attention to risk regardless and ignore completely disadvantaged group status. So what happens if we make pretrial detention decisions that way? Okay, so if we detain solely on risk with no consideration for group, and imagine that the judge decides to detain everyone with a rearrest risk of at least 20%, so 20% or higher. What's the detention rate for the disadvantaged group? It would be 75%. What's the detention rate for the advantaged group? It's 50%, okay? So what you would see here would be a disparity in detention rates from a race-blind detention rate, from a race-blind detention rule, that results from, not from a biased algorithm or biased data, but from biased circumstances, okay? So, so what you get with an unbiased algorithm and unbiased data in this case is a disparity in detention rates between the disadvantaged and the advantaged group. You can imagine other candidate definitions of a fair detention rule, for instance, things that would lead to perfect equity in detention rates, okay? So imagine we have some access that distinguishes more fair from less fair detention outcomes. At the top, you could imagine perfect equity. We know that groups are not born different, okay? So when we see differences, when we see anything other than perfect equity in detention rates, we know there's some unfairness somewhere in society, okay? So the aspiration is perfect equity. What we actually see in the detention rates with the unbiased algorithm with the unbiased data are disparities between the advantaged and the disadvantaged groups. And the wedge between perfect equity and what the unbiased algorithm with unbiased data gives here, that wedge comes from structural disadvantage. That is, bias in society that is external to this decision, or put differently, that's external to the algorithm and the data in this case. So I think the key point to take so far from this is the importance of not confusing structural disadvantage with data or algorithm bias. And this is not a statement about what's fair, but rather it's a statement about what the source of the problem is. And in particular, if you lose sight of the role played by structural disadvantage in the background here, you're at risk of looking to fix the problem through the algorithm when the actual problem is really upstream in society itself, if that makes sense, okay? So that's, I think, the first lesson to take from this very simple sort of framework in this cartoon example, okay? So now we can turn to the alternative to the algorithm, which is the judge. So what might a judge do? Okay, so let's suppose that the judge has access to exactly the same data that the algorithm has. For now, let's assume that. Okay, and is making the same sort of prediction decision. Well, what do we know about judges? We know about judges the same thing that we know about all human beings, which is that the propensity to in-group favoritism and out-group bias is deeply ingrained, okay? And so we have every reason to expect that judges on average are biased. So now imagine for the moment the judges were able to predict as accurately as algorithms. We know from behavioral science that their predictions will actually be less accurate than algorithms. But suppose for the moment that the judges are predicting like algorithms, they're using the same data as algorithms are. There's the same structural disadvantage sitting in the background that causes the disparities in the data themselves in terms of the prevalence of prior record for the disadvantaged group. Now the judge is making detention decisions here with some bias. What is the judge going to do? the judge's bias is going to lead, what would it mean for the judge decisions to be biased? What it would mean would be, if the judge's official rule is I'm going to detain everybody with a rearrest risk of 20% or higher, it would mean for the judge to apply that rule differentially for Black and white defendants. So the judge might apply that rule with perfect fidelity for Black defendants and something less than perfect fidelity for white defendants, or disadvantaged defendants and advantaged defendants. And similarly, for low-risk defendants, where their rearrest risk is below the detention threshold, for the judge to apply it selectively there. So the judge applies it consistently for advantaged defendants, but inconsistently for disadvantaged defendants. So they're unusually lenient towards some high-risk advantaged people, and they penalize some low-risk disadvantaged people. And so even though there's no actual difference in rearrest rates, what we would wind up with here is a detention rate of 80% for the disadvantaged group and a detention rate of 40% for the advantaged group. Or what's the implication that this simple example is leading to is give the same data to the judge, right? The same data that the algorithm has to the judge, and now layer on some human bias, which we expect to be there on average from a large body of behavioral science and economics research from decades. And what we would see is perfect equity is the standard that we're aspiring to. Unbiased algorithm with unbiased data gets us here, where the wedge is structural disadvantage. Biased judge with unbiased data gets us less fair outcomes than the algorithm, where the wedge here stems from judge bias. Okay, does that make sense? Okay, so the humans are adding bias above and beyond what the data would lead you to do just based on the predictions themselves. That's sort of the key lesson here. Okay, so this is a way to see why the algorithm can turn out to be less biased than the judge, because the human is adding their own bias on top of the conditional on the predictions and the data. So don't confuse biases and structural disadvantage. The algorithm can remove bias that humans add for this reason, because the algorithm itself doesn't have any intrinsic in-group preferences, okay? And then the caveat that I want to just briefly make here that we can return to during Q&A is the one caveat here is the algorithm can remove the bias that the humans add if we're actually predicting, like in the pretrial example, if we're predicting the defendant behavior. If the judge and the algorithm are both predicting the same thing, defendant behavior, then the algorithm can remove bias that the humans add. That need not be the case if instead we predict not the actual outcome like defendant rearrest, but the judge decision, the human decision, right? And we see lots of examples in policy relevant applications where people, I think without thinking about this enough, build an algorithm that is not predicting some ground truth outcome like rearrest, but rather essentially automating a human decision. And that can lead the algorithm to propagate all of the biases that are there in the human decision. Okay, so with that caveat, we've just seen that the algorithm with unbiased data, the judge with unbiased data, the algorithm can reduce bias in the judge decisions. Okay. Now let's relax the assumption. Let's relax the assumption that the data are unbiased, okay? So suppose that we're building an algorithm to predict defendant rearrest, and now we have a data set. So this is exactly the same little cartoon data set that I showed you before, but now we live in a world in which the police are biased against disadvantaged people, okay? So advantaged and disadvantaged people with prior records actually commit new crimes at the same rate of 20%. But when police come across advantaged people committing crimes, they sometimes let them go. So the rearrest rates that we see for people with prior records are different now between people in the disadvantaged and the advantaged group. And similarly, police bias manifests itself among people without prior records, where the police sometimes arrest disadvantaged people even when they haven't committed a crime. And they don't do that for people in the advantaged group. So now we've got bias in the data, okay? So how do we think about bias? What will happen in this case? Well, the obvious thing to note, right? The obvious thing to note is if we simply just built a prediction model without any consideration of the bias in the underlying data, the bias in the dependent variable propagates to the predictions and the subsequent decisions in the same way that we saw with the care coordination paper before. Okay, so that's the obvious thing to say. But the thing that might be somewhat less obvious, right? The thing that might be somewhat less obvious is that there's something else that you could do here instead in principle. There's something else that you could do here in principle. And the other thing that you can do here instead is in a world in which you know that the data are biased, right? You know that the arrest data are systematically biased against disadvantaged people. Essentially, what you can do is, if you sort of think about what any sort of decision-making framework for an algorithm is in one of these policy applications, it is basically rank ordering people on the basis of some predicted outcome, and then drawing some threshold and assigning some policy or treatment to everybody above some threshold and not to the people below it, okay? And in principle, what we can do in this case is, if we know the data are biased, we can set different detention thresholds for advantaged and disadvantaged populations in ways that undo the effect of the bias in the data, okay? Or another way to sort of say this is that algorithms come with an equity knob. Now, just to take a step to the side here, right? One thing that's sort of interesting about this is this flies directly against everything that current anti-discrimination law says you should do. It explicitly uses race in making a criminal justice decision, right? And the law says that we can never pay attention to race in making criminal justice decisions because the law was written in a world in which all criminal justice decisions were made by humans. And we don't know what humans are doing, and so we can't trust humans, and so we want to blind humans to race in all cases. That's the only way we can be sure humans won't discriminate. But the way that algorithms discriminate or can undo discrimination is very different, right? And so I think one of the key things that the field is going to work through over the next several years is how to think about updating regulations around discrimination to deal with the new ways that algorithms discriminate that are different from humans. Okay, but so going back to our little simple framework then. So what does it mean for an algorithm to have an equity knob? So here we've got, suppose that the judge and the algorithm both see the same data, okay, and the data are now biased. The biased algorithm so if we build an algorithm with biased data, the biased algorithm will now lead to even more unfair outcomes than an algorithm with unbiased data. So we've got structural disadvantage, and then we have shared data biases for the algorithm and the judge. They're both seeing the same data. And then on top of that, the judge adds their own bias in the decision-making as well. You give the judge all the p-hats, and then the judge adds bias on top of that, okay? But because the algorithm has an equity knob, we can set different group thresholds to get back to what an algorithm with unbiased data would give us. So we can undo the bias in the data. And in fact, in principle, we could even go all the way back to perfect equity to undo the effects of structural disadvantage as well, okay? And so the key takeaway here, I think, is algorithms have an equity knob you can turn. It's and I think importantly, we can turn the equity knob on the algorithms in a way that we simply can't with human beings, because we just have no idea what humans are doing and very limited ability to change what humans are doing. Okay. Now, the final thing that I wanted to close on, and then I'll stop and we'll open up for questions, is I wanted to just give you an example of what this looks like out in the real world that my research center, the Crime Lab at the University of Chicago, has been doing. And so going back to the pretrial release example, we built an algorithm that tried to pay attention to all the risks.
Can I pause you for a second?
Yeah.
There was a question in the chat. Arushi wanted to know, how do you implement the different thresholds? Would that still be done by humans?
Yeah, so the implementation of the different thresholds, is done by humans based on some human prior belief about the nature of the bias in the underlying data, combined with some human policy objective. Okay, so if you sort of go back to this little framework right here, right? If the policymaker has some sense of how much bias there is in the data, the policymaker, and together with the algorithm constructor, decide how much to turn the equity dial on the algorithm to increase the detention risk threshold for the disadvantaged group to fall anywhere on this continuum right here. So anywhere on this continuum, that part of the decision making is based on human beliefs about the amount of bias in the data. And then in principle, you can also further turn the equity knob to undo the role of structural disadvantage out in society. That's a normative policy decision that also stems from the humans. So that's just to say there's nothing in machine learning engineering that's going to give you the answers to those two things right there. Does that make sense?
Thank you.
Sure.
And
Okay.
I think you answered this already, Jens, but Emma wanted to know, would that be legal?
Would that be legal?
Yeah, but I think you already touched on this.
You answered this already right after I asked the question.
Yeah. I just, as a going to the real world, I mentioned this. I gave a like a closed door talk to someone in the mayor's office in a large anonymous American city, and I mentioned this idea, and they literally screamed. So working out in the real world is very interesting in that sense. So we actually built a pretrial risk algorithm in a large anonymous American city of 8.7 million people. This is even funnier if you had any idea how long it took me to pixelate this image. And the first thing that I just wanted to point out is, like, where did most of the work go? So it wasn't actually in the machine learning engineering, interestingly enough. In many applications, a lot of the work would wind up going into thinking really hard about what the dependent variable would be. In this particular case, that was an easy decision because state law told us what it had to be, right? So that's idiosyncratic to this application. But there were lots and lots of conversations around what predictors to use. And a lot of those conversations were motivated about concerns to address bias. Should you use arrest versus convictions? In a world in which the police force in this anonymous city might have done lots of stop, question, and frisk for many years, how do we think about using arrests or convictions for minor crimes like marijuana possession? And should we do things like put time limits on people's prior record, ignoring arrests or convictions that happened beyond some amount of time in the past? And then the other thing that was enormously time consuming as part of this project is, the algorithm doesn't get deployed. The algorithm doesn't make decisions. The algorithm is an input into human decisions. And so it's only going to translate into any social good if the judges pay attention to the algorithm's recommendations. And so we spent a lot of time talking to judges about what they expected or wanted to see in a statistical model and user interface to help increase the chances that they'd actually use the tool. So what did we see? So New York City, when we worked with them to build this algorithm, they'd actually been using an old algorithm that had last been built in 2003. And so we were doing this in 2018 or 2019. So when you hear things like zombie predictions, people build algorithms and don't update them, that really does happen in the real world. You can see that the algorithm that they had been deploying in this large anonymous, pretend that this actually says large anonymous American city instead of what it actually says. You can see that they were recommending a fairly low share of all defendants for release, okay? And you can also see that there was a large disparity in release recommendations between blacks and whites. We build a new algorithm, we deploy this, and the new algorithm that we build recommends about 84% of defendants for release for black and white defendants. And sort of just to pause on this for a second, whoops, what did I do here? Oh, look at that. Okay, hold on. It's much better when you can, actually, let me just, in the interest of time, let me just cut to the, so you can see that there are large, okay. There are large gains in overall release rates that disproportionately benefit minority defendants in New York, okay? And you can also, so one fairness gain here is simply the overall increase in release rates. The other fairness gain is relative from reducing the disparity between blacks and whites. So what happens when you deploy this tool out in the world? This is the bittersweet coda. The bittersweet coda here is the judges in New York City take a release algorithm that that recommends 84% of defendants for release with no disparity, and they wind up releasing a substantially smaller share of defendants in both groups and reintroduce about a 3 percentage point gap between black and white defendants. Okay, and so I think, you know, hopefully what I've communicated here is, as you're thinking about algorithms and the risk of bias, or if you think about the introduction of algorithms into policy applications and concerns about equity and bias, there are risks associated with deploying algorithms that come from failure to consider fairness issues. And those can manifest themselves in blueprint errors of all kinds. And that's a problem, a big problem with algorithms, because those blueprint errors get propagated to millions and millions of people because algorithms operate at such large scale. On the other side, there are opportunities that come from algorithms giving us the potential to eliminate bias by humans, that humans add on to the data, the chance that we can adjust and undo the bias in the data in a way that we can't change what the judges are optimizing, the fact that it's easier to uncover bias in algorithms, and it's easier to fix bias once we find it with algorithms, okay? And so what I'm trying to convey here is some more balanced sense of what algorithms imply for fairness, where you can see that they're not unambiguously helpful or harmful, but there are risks and opportunities relative to the counterfactual here of human decisions. So let me stop there and see if there are more questions.
Marlene, you had, I think, a good question in the chat.
Yes, thank you very much, James, for this presentation. I was just wondering, actually, I'm thinking if I am right to think in this way. Like, if we have a relative threshold, maybe it's not, not necessarily sufficient, like to, unless we identify like the true reason of observing such a bias in the data. Like, if I take the example of the police officer that may be biased against the disadvantaged group, and if this type of bias is more like a test-based type of discrimination, maybe if we change the threshold, it will be kind of a game. Like, they will try to push more disadvantage into jail, basically to counteract the differential threshold that we put. So
yeah, let me great question. Let me try and let me respond with two points. One is, I think this is implicit in what you said for starters, which is that the adjusting of the thresholds is helpful only to the degree to which you have you can have accurate beliefs about what the bias is in the underlying data. And so I think that's one sort of intrinsic challenge to thinking about using the sort of, how far do you turn the equity knob? So then the second point that you're making is a really important one, which is when we, it's a larger point about, another way to say it is general equilibrium effects out in society from when we deploy algorithms, okay? And, you know, one this is essentially like a spam problem is what you're describing, right? Where we implement the algorithm and then the humans on which the algorithm was trained change their behavior in response to that. And I'm looking at Jan and Ziad and Sendel and wondering if we are going to talk about things like spam problems and GE challenges with algorithms at any part during the workshop, or is that not on the docket this year?
Josh will almost certainly talk about it when you.
Josh will talk about that.
I think the other thing I just add, Jens, to what you're saying, is that one way to think about the differential threshold is you set it with respect to priors and you set it. But just the other way to think about it is you just have a preference for equity. If you have a preference for equity, it doesn't matter, even if the data is completely unbiased. I think Emma makes the point about affirmative action. Even if the data is completely unbiased, you may just choose to set the threat. And so one way to think about this is just, it's not even about responding to police officers, or it's just saying you have an objective function that is defined not just on outcome, jail, etc., but is defined on racial equity, which is reasonable to have. You have that. And then you just set the threshold to get the equity outcome that you want. And one way to think about that is there's nothing new about setting the threshold. In every ML algorithm that you put in any classifier, there's some threshold being set anyway. So there's really, this is almost a different way to say everything Jens just said is, if you care about equity, put it in the objective function, and then you'd optimize that along with predictive accuracy. I think, is that a good way to say it, Jens?
And the only sort of small thing that I would add to that is the reason that I was distinguishing, I mean, maybe unhelpfully distinguishing between turns of the equity knob in response to beliefs about bias in the data versus a preference for equity is, I think, in the legal discussions around these issues, there would be big differences within the legal system that we have around how the legal system views different justifications. But you're absolutely right.
I think Noam had a question.
Noam had a question too.
Yeah, I was just curious. I was actually struck by the data kind of showing that the judge decision-making seemed affected by the output of the algorithm. And I was curious how binding it was, or if it was sort of built into some other set of information they were using. And then does that mean that the judges might trust the algorithm more than they might trust other heuristics or sources of information? Is that something that you're testing or have tested? Because that seems like an interesting, if people trust the algorithm more, that could really help undo human biases. So that seems really interesting.
Yeah, the algorithm's predictions and recommendations are not binding in New York. What is true about the algorithm that we implemented is that it was more predictively accurate than the algorithm that had been deployed before. And judges were actually releasing, and so I think another thing that I hadn't sort of appreciated the importance of before we did this out in the real world is that there's the algorithm which spits out a bunch of p-hats, and then there's a decision-making framework that maps the p-hats into some recommended action that you give to the human. And there were two things that were different in the New York City context. One was a different set of p-hats, and the other was a very different mapping between the p-hats and recommendations. And the mapping recommendations turned out to be more aligned with what the judges had been doing in practice prior to that point, if that makes sense. And so I think both of those working in tandem rather than sort of brute force requirements, presumably, are what got the judges to pay attention to the new tool.
Jens, if you have energy for one more question, I think Lindsay had a good one. And then we can call it a live stream after that.
Yeah, I was just wondering if we should take your results to suggest that we need to rename the field to human plus algorithmic fairness rather than just algorithmic fairness. And if you would wanted to expand on that, I'd appreciate it.
Yeah, it's a great. I think that would avoid an enormous amount of confusion in the discussion. You know, I remember talking to the deputy mayor of some big city that I won't name, and you know, we were there to talk about the idea of building some sort of machine learning tool to predict pretrial release. And the other government person there, like introducing me, said, like, this is the nerd from the University of Chicago. He wants to talk to you about building this machine learning thing as blah, blah, blah. And the deputy mayor, like, the very first thing they said is machine learning. Oh, Jesus, those are biased, right? And the previous tool that they'd been using was a logistic regression, basically. And you could sort of see, like, in that moment, the confusion that you're hitting on exactly, right? Which is this imagining that the problems are actually, where the problems get introduced is from the change in the statistical procedure, rather than from all of these other kind of human decisions that sit around it, both on the algorithm build side and on the algorithm use side. Because in I think also implicit in your question, for policy applications, like, nobody wants an algorithm to be the final decision maker for pretrial release. And for lots and lots of policy decisions, we are, for the foreseeable future, I think understandably and appropriately, going to have these tools not as deciders, but as decision aids. So there will always be sort of the human as where the buck will stop, rather than the algorithm itself. And I think that frame of human plus algorithmic fairness, I think, helps you see where a lot of the problems come in, but also where a lot of the progress can be made if we get those parts of the system right. That was a long answer, but I'm not sure a helpful answer. But thanks for having me. And I think next is Yun and Sendal in office hours. Is that right?
Yes. So first, I'll just remind everyone of the festivities for tomorrow. So Emily, I don't know if this is on the schedule, but we decided to live stream my talk at 10 tomorrow morning on healthcare, although it probably won't be very good. So for those of you who are listening on YouTube, I'd probably suggest not bothering. There'll also be Josh Blumenstock, whose talk will be much better at 2 p.m. So definitely tune in for that one. And for those of you who are not going to office hours, the Gather room is open with all of the attendant games. So we'd encourage you to go do that, unless you're going to office hours, or maybe in combination with office hours.